Okay, good. So welcome everybody. It's my first webinar also that I give at CSCS, despite me being several years here. I'm Vasilis Karakassis, and I have been like computer scientist and then group lead. And I'm going to present ReFrame, which some of you might have heard of, some of you might have already been using it, some others may, it's maybe the first time that they listen to it. And it's a framework for system and application performance testing and validation testing. I'm going to talk a bit more about it. Yeah, I will go through the presentation with examples, and also I have a demo which you can, which is recorded, a terminal session, which you can then have a look on how things are run actually in practice in the exact examples. So, yeah, when I was trying to do that presentation, I mean, first thing is the question that came to my mind was, why should I bother? I mean, trying to be in the shoes of the audience, because we, if not all of us, but many of us have either been actively doing unit testing for our software, or we're doing some sort of that type of testing to test different components of our software. But that's not enough, and there are more to testing beyond unit testing. That's the first step. Unit testing is the first that you need to do, and you make sure that your software is well tested in that aspect. But then there are different levels. One is, which I'm trying to list in a way here that's not like more in an ad hoc way. So one is integration testing. How does my application behave as a whole, given different scenarios? So you have your unit testing that tests different components, but you need to test the application as a whole, how the different components interact with each other, and how your application, for example, behaves on different input. And that's especially true also for scientific applications, where you want to test different scenarios and validate the results. That comes also to validation testing, especially useful for the scientific results, because you might be doing a change into your application and then you might get incorrect results, which this cannot be, for example, easily in specific cases spotted by unit testing, because it might be multiple components that they interact and they finally produce a wrong result. So you need somehow to write tests that catch this. Then regression testing is another type of testing. And the typical example is, did my application experience any application or functionality performance regression when I either did an upgrade, or there was an upgrade on the system I'm running, on the systems I'm running on, and so on, or in the software stack that I'm using. So there are different sources of regression that can be either inherent to the application or external to it. Another important, very important aspect, especially for us that we're doing high performance computing, is performance testing. And that has several aspects, and basically boils down to, how does my application perform on various systems, various architectures, various compilers, and so on. And we might need to figure out specific paths to optimize, or to basically will guide our design of the application if we want a high performance computing application. Scaling testing is another aspect of performance testing, and we want a way, for example, to check how our application performance scales. And another important aspect, especially also, even if you're a software developer, but especially if you provide software stack and set of applications to end users, is performance exploration. And for example, what is the best configuration to run my application or application X on a system? And you might have to try different build configuration. You might have to try different ways of invoking the application, and you need to do that in an easy way. So, as I said, unit testing is the basic building block, but it's the basic, but it by itself it's not enough when we talk about testing. And although there are very good frameworks for each language that you choose to write your software, there are very good frameworks for testing, and unit testing especially. There's not. If you go beyond that, usually you have to fall to the good old shell script solution. And I'm not saying that against shell script. It's just shell is great for what it was designed for, and shell is great for executing commands and for writing some system scripts and so on. But when you try to build something more complex, then you hit its limitations, which is not fully blown programming language. So usually there are two ways that I have seen personally this happening. Usually users either write customized shell scripts to test their applications on various systems, and basically every team redoes the same works. Like I'm checking which system I am, how I'm going to load my environment, so on and so forth, how I'm going to interact with the various schedulers, how I'm going to interact with the environment, and so on. And that's really customized shell script written for each system and for each application. Or other more advanced solutions that I have seen is that you extend the unit test frameworks kind of functionality, so that you basically build the integration and performance test into with unit test framework that you have. But this has also its limitations. Is unit test framework was not designed for that type of task. So you might end up with having like non-portable solutions that you would have to adopt every time you move on to another system, and you will have also to maintain that if system changes and so on. And that explodes if you don't have just your single application, but you have to maintain more applications. And for example, when you want to provide HPC environments to users. So that was what I've incited us like 5-6 years ago to start with this project. We eventually called it ReFrame. Wasn't that the name when it started? We were not that imaginary back then. And essentially is a powerful framework that is designed from ground up to write portable validation, regression, and performance tests. That you can take your tests that run from your laptop, that validates your application on your laptop, and you can validate the same application or do a scaling test or performance test automatically on a different system, like a top 5 supercomputer, like Pitstain, for example. Here, I'm just listing a very few highlights of the framework. It has lots of features, and yeah, a slide would not be enough to list them or to explain them. So essentially what ReFrame is, it implements a Python, practically an embedded DSL somehow embedded in a DSL embedded in Python that allows you to write tests in high level and in a declarative way. So there's lots from those interested in the implementation of the framework, there's lots of meta class magic happening to have some fancy syntax there. And one key feature is that tests are composable by design, and you can extend and you can reuse them. So you can test one test that somebody written, and then somebody else can take it and just derive from it and extend it or change it. It supports multi-dimensional test parameterization. So you can basically, from a single, let's say, test template, you can generate hundreds of tests that you can check all different aspects of your, or different combinations of your parameter space. Yeah, it supports also resource sharing through test fixture. I'm going to show examples for all those. It can auto-detect the processor topology, so then you can have informed decisions on how you tweak your test based on the number of cores you have, the amount, the caches, or the type of caches, or also the size of the caches, and so on. Of course, it supports parallel execution of tests, so you can just spawn multiple tests and has a runtime that will efficiently schedule all those, and you don't have to just pull them by yourself every time to check, this test has finished or this hasn't. So it really takes care of it. It supports native and containerized run, and you can have also performance logging. That's especially useful for teams that have to have codes in production. And we use that a lot at CSCS. Another cool feature, especially useful for development, is that it has also seamless integration with GitLab CI/CD pipeline. So you can use it to generate a child pipeline for you. I'm going to briefly touch on this topic. So as I told you before, it was designed and developed by a small team back in 2016, mid-16. no, first, second quarter, if I remember correctly. And the goal was to replace a basket-based regression testing framework that we had at the time, and it was very difficult to maintain and to scale and to basically add tests and convince also ourselves back then as a team, but also others in the center to contribute tests. So that's how the idea came up to rewrite something. And we have faced the problem. We knew what was problematic with this. So we really focused on portability and on hiding the details of the system interactions. So it was first publicly released in May 2017 on GitHub. And since then it has, I would say it has flown. So now we have like 42 contributors. Of course, they're not CSCS. It has a growing community, 78 forks and already 156 stars and several releases. And is this used both by academic institutions like us, like either university clusters or like labs like in the US, big labs, or like CSCS supercomputing centers, as well as industry around the world that they use it also for performance exploration, both in the, let's say, classical, traditional HPC, but also in the cloud. We have a repo there where we have our CSCS tests publicly available, so as to be as a reference. And there is also a Slack workspace with already more than 190 members, where you can join for updates and support if you want quick answers, and if you hit somewhere and you don't know if it's a bug or not. And yeah, occasionally we have some community calls to talk to the community. So now I will jump into how a test looks like. But before discussing the example, here I have a link. We're going to share the slides afterwards. So here is a link where we have all the examples that I'm going to show here. And there is a demo run of all the examples here. In the Ask Kinema, I can just click on that so that we have it. Okay, I need to switch just a moment. I need to share my whole screen. No, okay, now we'll share this one just to show you a bit how it looks like. And then you can, this link is valid for the next 7 days. So you can click on the download to get it, but you will not get the video, of course. You will get like a metadata file, which using this Ask Kinema program. It's a command line tool. You can replay it in your terminal. I'm stopping this here, and I will come back to it as we go through the presentation. Let me share again my screen, and let me find it. I think that's it. Okay. Can you see my screen now?
Yes.
Okay, thank you. So here is a pretty simple test. Now the whole presentation will take the stream benchmark as an example, and we will build on top of it for a very, very simple thing that only validates the solution, as this the one that I'm showing here. And we will take it we'll make it flexible enough, and then we practically will go from our current machines, our current laptops, up to run it on Dane, several different compilers and so on, with no changes practically to the final test. So here is how a very simple and base test in ReFrame looks like. So you have some import things that you have to, some modules that you need to import. And basically, tests are simple classes with some statements here in their class body, and they have to be decorated. So, and then, for example, all tests need to have valid systems and valid program environments. This is basically, you scope the test for specific system and environment specs. We're going to see that more in practice. Then you provide some build instructions. Not in every test this is necessary, but in this particular one, we need to build the source, which say now use the single source means practically you just invoke the compiler command on a single source file, which you provide with a source path. And then every test must have a validation routine, which basically it's a basic function that's specially decorated. Okay, here I missed that because this should be, I have a, oh, just a second because I messed up my screens. Wait a second. Okay, this is it. No, I'm sharing the wrong screen. Wait a second. Okay, no, that's the right one. Okay, now I should be fine. So this, I've done an error in copy paste. This should be indented one level to the right because that's a method of the test, but that's my fault. So that's how a single test looks like. And here is how it is structured. So you have a directory with tests that can be in directory, and in there you have a directory, but that by default is named SRC, which has the test resources. It can be a source file, but it can be input files. It can be anything that the test needs to run. And then you have a Python file which contains a test, but it can contain multiple tests. So the top level directory can contain multiple files. And then, as I said, you can change also the resource directory, and the test file can define multiple tests. So it's really flexible, and you have a choice on how you define your test the best way that fits you. Now, one thing is that ReFrame is not a shell script generator, although eventually you will need to generate some scripts, especially if you want to interact with batch scheduler or to set up an environment to run the test. There's no test logic embedded in those scripts, and that's made on purpose. We wanted to make very lightweight that thing, and we didn't want to go down the path of this cell does it like that, the other cell does it the other way, and so on, and rely on features of the cell we choose to do complex stuff. We want to avoid that, and we want to have all the logic that is more complex into Python. So literally the code of the generated test, for example, in that particular example, to build that stream test that just shown, is like that. It has some boilerplate, which actually could also be simplified, but that's how it is now. And then just the command. Now, there's no error checking in the sense of, oh, okay, if this command failed or not, and what I should do there. That's part of the logic in the framework and in the test. And the same is of what is going to be executed, which is essentially a bash script that executes the generated executable. The reason that this is a bash script and it's so simple and silly, looks like silly here, is that the same test can generate a completely different job depending on the job scheduler if you use one on the system you are and on the configuration. So that's why you have a shell script here. Now, stream, of course, is a performance test, and we want to assess its performance. But the first thing is, the only thing you need to do to convert the performance test is to define a special function. Again, this should be that in, and I will fix the presentation, to extract the value you want. So here we want the copy bandwidth, and we have a regular expression here with a capturing group that basically you select the capturing group here, which is the capturing group 1. And basically you can also name it, and you can use the name if you want to, and convert the result you took, the string you extracted, into a float. So then your actual performance value is a float. If any error happens, then the test will abort the test, but not the framework. So that's, the name of the metric is by default, the name of the function, and this can be changed if you want to with a decorator argument here. But perhaps, I can show you a bit how this runs, because to get a bit of the feeling, I will stop sharing and start the. I will share the other screen with a demo. Okay. Let me make it. Can you still see it?
Yes.
Okay. So here is the test that I actually shown you. And yeah, with -C, you select the test, and -L, you list them. So you see just the stream test, you see some info. You can also do the concretized version. I'm going to show you, I'm going to explain what this is, and then you run it. And basically, yeah, this is how it looks. And I can, here is the next test and someone that I've just shown you. So this is how it goes. And then you can also, for example, use the performance report, and again, you get the bandwidth you got. The bandwidth is so slow because it's a single threaded. We're going to expand it. So I'm stopping this here and continue with the presentation. Okay, because now we're entering into the configuration. Because when you take ReFrame by default, it will run on your system no matter what, because it assumes a very minimal generic system and environment that you can't do much. Essentially, when you want to test things, you need to properly configure it. And there are lots of aspects of the framework that can be controlled through the configuration, either through the environment variables also and command line options. So here, for example, is a configuration that I used and in the demo for my laptop. And basically, you define that kind of thing that's called site configuration, which is a big JSON dictionary with sections in it. I'm not going to go into all the details, but essentially you define systems, and in the system, you have an attribute that's called host names, which is a list of valid host names that ReFrame will try to match when using that, to identify which configuration entry to load when it runs on the system. And then you define partitions. In that case, just a local one that uses a local scheduler, local launcher. So no Slurm, no MPI run or no parallel launcher, etc. And here you define the environments if you want to test your, you want to test for this system or this system partition, which eventually you define them in a different, okay, I have annotations here. And then you define them in a later section in the configuration. You give a name, what is the compiler command to use, and you can add arbitrary features or extras, which then you can select in a within your test. So in the way that you define your environments, you make it consistent. Eventually, you can use this extended syntax that I'm going to show you in valid systems and valid prog environments that you can select tests and based on features or extras and specific values, and you don't have to match them with the name on the environment. So here is exactly what I just talked about. So here we say that this test is valid only for those environments that they define this open feature. There is also like a community discussion whether we kind of standardizing those features so that we can have change configurations, but that's in the very, very early stages now. And one thing we changed now in this is the valid programming environments. The other is we can define now performance references, and you define it through this variable that's called reference, and then the special dictionary. So you have the system name or system partition. And then you have the performance metric, and then a tuple that has the baseline and the lower threshold, which expresses the fractional item, fractional number over the baseline, and the upper threshold, in this case none, and the unit optionally. And we further want to extend the test now. We want to change the weight bits because we want to first increase the stream array size to make it big enough. And the other thing is that we want to pass the OpenMP flag. And you can do that basically by changing the different phases of the test. These are called the pipeline of the test. I'm gonna have a dedicated slide about it just in a second. So here we say before you compile, execute that function, which practically takes the OMP flag that's defined in the current environment that's now being tested, and basically applies it with an optimization level, and it adds some flags. And before running the test, you now take the processor topology that's auto-detected from ReFrame, and it will just get the number, of course, and then set up the environment variables accordingly. And then we run the test. We will see that in a moment when I switch again Windows to show you the demo. So eventually, if each ReFrame test goes through a series of well-defined stages. That actually, yes.
Sorry to interrupt. There's a raised hand, so before we move on. So
may I ask you to go back a couple of slides when you there was a JSON file where you specified more. Go back.
Here?
Yes. So it's actually possible to specify deep, because here in every, let's say, item of the dictionary, you have one key and one value. Now, what actually would be interesting to see when you generate benchmarks to have different options and to generate different benchmarks. Is it possible to do it in this context?
You could either do it through environments, or you could, one option would be, if you want to, for example, compile, I guess you mean you want to compile your applications differently with different flags?
Yes. Okay,
that's, in that case, probably, I know teams that they're using like Spack, for example, to try different compilations and generate different, for example, modules, and then have another test. They have one test that basically generates the Spack builds, and then perhaps another test that depends on that uses the exact spec that the application was built with.
Yeah,
it's either way, actually.
Here, if you would like to use different compilers, say once with GCC and another one with Intel. I mean, could you do it?
Yes, here you can do, you can define new environments here, and then basically when you have your environments here, like here I'm testing GNU and Clang. And then for your other partition, you could have GNU, Clang, Intel. For example, you will see that when I show the configuration that I've written for Daint, where it has 4 or 5 compilers.
Okay, thank you.
Okay, so as I was saying, there is each test goes through a set of well-defined stages that execute atomically and in order. Atomically in the sense that while the test executes in that phase, it's not preempted by the runtime of the framework. And then you can attach arbitrary functions from your test to run before or after. And the runtime executes the test concurrently, basically interleaving the execution of those the stages of multiple tests. So you need to have lots of tests to see a benefit. And you can put also concurrency limits. And that's quite useful, especially if you execute locally and you might bother the users, or if you run on a cluster and you don't want to fill it in with your jobs. So you can put concurrency limits there. And the other thing is the runtime honors test dependency. So you have tests that depend on each other, they will be executed in the right order. And the dependent test will only execute if its parent has finished successfully, otherwise it will also fail. So here are the 6 pipeline stages. And basically there are 2 execution policies. One is the serial execution policy. It is not the default, but there might be cases that this is useful. And that's, for example, when you run a benchmark locally, for example, the stream benchmark, and you run it on your laptop, and you don't want to run different configuration. You don't want to, in order to get correct results, you don't want ReFrame to spawn like multiple stream benchmarks at the same time, because you will get failures without a reason. So essentially in that, it has lots of filing time. So it compiles and then waits for the compilation phase to finish. It runs the test and waits for the test to finish and so on. But if you have a system that is, for example, PitStain, or a system where we have a scheduler and you can sustain parallelism there, then you can use the synchronous execution policy, where ReFrame does not stop and basically asynchronously spawns jobs for compilation or for running, and then the runtime monitors the progress of the various tasks that they are on the fly, and then continues and finishes the pipeline of each test. And it's quite efficient. So, for example, here it's a run and how the pipeline progresses from the different phases, not of the test, but of the states of the pipeline. It's a bit internal this. And you could see here we have 2 remote partitions contained, each one allowing 100 concurrent jobs. And we also allow in that specific run up to 8 local builds of various tests. And you can see that, let's start from the compiling, which is this green little line. And so it's just 8 jobs, local builds there. And then you have in the running phase, you have actually 200 jobs that basically are submitted and maintained by ReFrame. And then as things finish, you see also this band going towards down. And that's the progress of the pipeline. So just to show you that it really, I mean, if you have lots of tests, like here we're running the full production test suite, which is about 700 test cases. And essentially it fills up the concurrency. One very interesting feature of the framework is that you can define test variable. So, and everything in the framework that I've shown you before, like the valid systems, the reference, the etc., all are defined as variable. So is a special built-in in that DSL that basically when you define a variable in such a way, it enforces type checking on assignments. So here, for example, we define array size as integer. So if in the test we're trying to do numiters equals foo as a string, then you will get an error. So you can catch errors in your test. And the other big thing is that it can be, you can also assign a default value as well, like here, but the default value might be left empty, in which case the variable is required. So if a test does not define it in any sort of way, then it will fail. That's also good, especially if you want to compose tests. And then you can set it different from the command line. So here you can say -s stream test, or the name of the test, and that's optional, numiters equals, for example, 100, and change the variable on the fly. That's quite useful. And the cool thing is also that in your various pipeline hooks, the variable is accessible as a standard object attribute. So it is actually eventually a standard object attribute. So here we set the stream array size from the variable, and same for the numiters. Another very useful built-in is the parameter. Parameter is when you define a parameter, basically you parameterize the test, and you define different variants for the test. Now, every time you have a statement as a parameter here, it adds a new dimension in the parameterization space. So eventually you have an external product of the various dimensions. But you can, for example, you can inherit parameters from another test, and you can either filter them or suppress them. And that's also useful in how you can combine tests. And of course, parameters are also accessible as normal attributes. And here, when you access them as self.lm type, in this case, it will have either float or double, depending on the actual instantiation of the test. So actually, this test is going to be instantiated 2 times, one with double, one for float. And imagine you can have multiple parameters. We have a second, we will see later on with the second parameter how it looks like. And when you try to list the test, you will see, for example, stream test, you will list 2 tests. So ReFrame generates out of one single test that you have written here, it generates actually 2 checks. And you can see the parameter here. So you don't have to rewrite anything or something. It has standard syntax. Now, another interesting feature that's also quite useful are fixtures. I don't know if you are familiar with test fixtures from unit test frameworks, but essentially a fixture is something that manages a resource that you need also to do something with it, perhaps to set it up and then tear it down at the end. And it has also a lifespan. That's a feature of the fixtures. It's something that manages a resource and has a lifespan, which we call it a scope. So the same in ReFrame, and except that, for example, those that are familiar, for example, with PyTest, fixtures there are functions because they're the tester functions. So the same idea as here, ReFrame tests are essentially classes, and fixtures here are also other ReFrame tests, normal ReFrame tests. Any test can be a fixture of another test. And fixtures have scopes. So you have the session scope, and in that case, the fixture will be executed once for the whole run session on any valid system partition or environment. It doesn't matter. As soon as there is one valid system and partition environment, the framework will pick that and run the session fixture, and it will stay there for as long as the whole run lasts. Partition, then the fixture will be executed once per system partition on any valid environment. Then you have environment scope, where the fixture will be executed once per system partition and environment combination. And the test. The test fixture is private to the test, and it will be executed every time the test is executed. Nice thing is that fixtures can be also parameterized. And if a test uses a fixture that's parameterized, this implicitly parameterize the test itself. I'm going to see here, I have an example. So here we split the stream test in two versions for the sake of showing it, but also it's a useful approach. And if you want, for example, if you have a test that has a build phase and the run phase, and you want to parameterize essentially the run phase, it's better if you split the test. So you do avoid redundant compilations. So in this case, what we're going to do is basically split the test in two. We have the stream build. It's as a simple ReFrame test, except that it doesn't have the decorator. It could have it, but we don't want to run it independently. And we just say that's a compile-only regression test, so it's not going to have a run phase. Same here, all the things we had before, nothing changes. The setup build is exactly the same. And then you have the stream test itself, which basically defines a fixture, which is called the stream binaries, that basically says this is a fixture of that class, the stream build, with the scope environment. So ReFrame will basically, I'm going to show you later on how it's going to generate all those things. And then goes as before, except that beforehand, you need to find the executable, because the executable is produced in the stream build. So actually what you do, you access it through the fixture handle here, stream binaries. And actually there you actually access the whole test that has run, because eventually this is a test that you depend on. Stream test depends on the stream build. And this test has run before you start the stream test. So then you can access all its variables or all its state. And by accessing all its state, then you can access, for example, the state directory. Yeah, here I'm introducing a new term, but I will refer you better to the documentation for that. So every test has its own stage directory where it executes, basically. So you access that, and then you access your, you construct the path there, and you get your executable for the stream test. And here, for example, is what are the tests that it generates. For example, here you see that the stream test with the fixture stream binaries with a lem type float depends on the stream build, a lem type float with scope. Here you have the system spec, Trezor default, that's my laptop, and the default is the default. This is how we name the main partition, plus GNU. And then you have another test, because it eventually, you see that the parameterization is in the stream build, but eventually parameterizes your final test. And this is how, for example, you get another test. So this means that stream build will be scheduled first, and then the stream test will be scheduled. Now, for example, here we extend a bit the parameter concept, and we add another parameter, and that's this, by writing, for example, here a scaling test. So imagine that somebody has written the stream test, and you just don't want to touch it. That's fine. So you simply just define another test that inherits from it, and that basically inherits everything, also its parameters. So then we can add a new parameter here, num threads, and basically we have 2, 4, 6 by 12 combinations now. We have the 6 num threads values, and then we have 2 combinations from float and parameter, and from the lem type. And then, of course, we can set up our run. Another thing is, with another hook. Now, one thing with hooks here is that you have an arbitrary number of those, and they are also inherited. So here it has also all the hooks of the stream test, and then you just add another one, and then you can have another function as well to serve the purpose of a hook. The order of which they are defined in the code plays a role, because this is the order in which they are registered to be run. And here we just set the num CPUs per task, which is a built-in reframe variable, let's say, to the num threads. And we have now also, we need to add this test because it's a bit naive the way we have defined the num threads here, because we just say, okay, let's pick an arbitrary number. And if your system doesn't have enough cores, then simply skip the test with this thing. So we get the number of cores from the processor, we check with our current parameter, and we skip it. As I said, the downside is that we hard code the num threads. And there is a more flexible way to do it, which is, that's a bit advanced actually, but shows a bit the power of the framework. So actually we don't hard code anything, but we introspect basically the configuration essentially through the framework's runtime. So there we get all the partitions, and for each partition, essentially here we generate a set of combinations of partition name and the list of maximum threads it can have. So for example, for your laptop, you have like 8 cores, you will get 1, 2, 4, 8. If you go in a system that has 20, you'll get 1, 2, 4, 8, 16, and the maximum and 20. And here we just, have this parameter, we call it threading. And then we, again, with parameter, we call how we get the spec of the threading that we want. And the nice thing is that you can also format it nicely, because you don't care about, you only care about the number of threads, for example. That's why we just add this formatting function. And we unpack that parameter pack. And with that, we set the num threads, which is the second part of the tuple. And then we also set the valid system, because we get the system partition. So we scope that this configuration is for this specific system. I know it's a bit heavy, this one, if you haven't seen that, if you haven't seen ReFrame at all before, but it's very useful. And I'm going to show how it shows in practice. So we have a question. Okay, we have a question. Does this RT module detect the course threads from Slurm allocation or system info? So actually the auto detection happens before as at the ReFrame startup. And by default, it only auto detects local partitions. You have to set an environment variable to force the remote partition detection, in which case ReFrame will use the information, the configuration file, and submit a Slurm job to detect the actual node. And then it will cache it under your home directory .reframe, and I don't remember the exact path, which if that is present, it will use that. If not, then it will try to detect. And the reason for not having the default, the remote detection, is that it can take some time to do. I imagine that, the first time you do it, it will take some time. If you have like 4 or 5 remote partitions, then you have to wait for the job to get allocated. So that's why it's disabled by default, and then you can enable it. So I said before that allows you writing tests in a portable way and without touching the test. And that's provided you have written the test in a way that, as I have shown here, that is a bit, also the test itself will be system agnostic and use the framework machinery. But of course, you can also tailor a test to a specific system by checking the current system or current partition or current environment. For example, to set reference values or to do some specific tweaks, because to be honest, you will often you will need to do some really system specific tweaks. So here is, for example, how I defined for this example for this webinar, the configuration now for Daint. So I have a new system named Daint, have host names here, both Daint and DOM, which is our TDS. We say that you use module system. You didn't see that because my laptop didn't have a module system, but here I'm saying you use tmod 3.2, you can use lmod, you can use tmod 4, there are different values here that you can use. Okay, the login partition has nothing special except that it has these 4 environments. And then you have 2 partitions, the hybrid, which are the GPU nodes, and the multicore. And both of them use the schedulers layer. There are different values here that you can use, but this basically activates the ReFrame backends to talk to the scheduler. Launcher is srun. Depending on your cluster, it could be MPI run, it could be as another version of srun, and so on, MPI exec, etc., etc. And another thing is how partition is accessed, how you get access to it, to partition. And that's not necessarily a partition in Slurm. It's a partition in ReFrame's terminology. So here you get access through a couple of command line options. And now here are the environments. So for each environment, you have the name, and you can optionally have the modules, which are optional modules that load that environment. You have a series of modules as well. And then you define again which are the various CC and compilers. And you define different for example, the extras. Everybody has the feature OpenNP. So our stream test will eventually pick automatically all those environments for Daint. But for example, it doesn't pick the Clang environment on my laptop because I haven't configured Clang with OpenNP there. And here you see also the different flags. So for example, the NVC uses the -np, Intel uses QOpenNP. And then the way we have written our test basically reads that from the config. And here is exactly, I basically run this command on the TDS. So config my settings, which is the settings file I've just shown you with the last version of the stream we wrote. And you can see that the generated variants. So, so you see that the ReFrame generates a variant, not only for each parameter, like 36, 32 here, and then on the multi-core, you go up to 36 cores, but on the login nodes, you go up to 20, for example, and on the hybrid, you should go up to 12, I think. And that's automatically generated. And also you see that it generated different versions of the build fixture for each of the programming environment. And that's because we say that the fixture has an environment scope. So it will compile the fixture for each environment. And we haven't touched anything here. And yeah, just a bit of how these things are kind of generated, because that's interesting and you can play with it. It's good to understand it. So for each test, ReFrame generates multiple test cases. Even if you write a single test, it's not inside the test only how many test cases will be generated. It's also part of the configuration. For example, if I write the test and my system that I'm testing has 5 partitions and each partition has 3 environments, then ReFrame will generate 15 test cases. And if there's no scoping, if you don't scope down the valid systems, valid partitions, and valid environments. And so there is a step from your test as ReFrame gets it and loads it to when you get the actual test case that it will actually run. And that's what we call it, test concretization. We kind of borrow that term from SPAC concretization because it's very similar in the concept. So ReFrame has to figure out which are the tests, which combination are to be executed, because this is what eventually will be scheduled for execution, and this is what you get listed. And also it can be different, the concretization, based on additional constraints that you set, especially for fixtures in the command line. For example, if you have a fixture that is session scoped, and you scope with a system and the P option, then it will be concretized different. It will run in a different environment than it could if you wouldn't put a minus P option, because a fixture can run, and that type of fixture, a session fixture can run on any environment and on any system. As I said, ReFrame schedules test cases, not the tests. And you can see the concretized list of the test cases with a -L uppercase C option. And this shows you exactly what is going to be executed. For example, if I do that with a stream9.py, I'm going to see 192 test cases from, I don't remember how many were on my laptop, were way fewer, without even a single change. So it really allows you to do large scale things for that. And we have used that, for example, with some cool features. I will describe in a moment, where you can distribute a test over multiple nodes or repeat it and so on, and leverage this parameterization behind the scenes. So before closing, there's some things that I think I reported, but I don't have the time to touch on them. One is you can test containerized applications as well with the same test. And it's very, for example, we have in this link here in Chromax example, where basically you test different images and the native all in the same test without having to really saving you code. And how you can do that is setting in your test, setting the container platform to the image to use an image. And then you can imagine combine that with a parameter so that your image is a parameter, and then you can run with multiple images at the same time. So, and the ReFrame will emit the write commands based on the container runtime you will be using. We support, of course, Sarus, we support Singularity, we support Docker and Shifter behind the scenes. So it's again agnostic when you write the test. Yeah, and as I said, the same test can be used as both native and containerized version, because if container platform image is not defined, or if it's none, then it's gonna use the native version. Another cool feature that I know people are using is the GitLab CI integration. So there is a nice option that's called CI generate that basically will take all the tests you have selected with their dependencies and everything, and it will generate the GitLab child pipeline. And each test in that pipeline will run as a separate CI job. And then basically you have GitLab CI running your jobs. And behind the scenes, it uses the cache feature to cache between the jobs, the state directory. And also if you see the generate pipeline, it also uses some, I think some artifacts, which is like the report so that it can relaunch the test. It's some details. And another two new features that are quite interesting is that you can get a test and just repeat it n times. And with the ---- repeat option, or you can get a test if it's a single node test and you can distribute it to run on every single node. And please don't do that on Daint. But it's a part feature if you administer a cluster, if you like doing some sort of user support or like providing an environment. In that case, for example, you have a set of nodes that you want, for example, to run them benchmark on them, and you have a reservation, then just get onto that reservation. There's some option that you can do that from the command line, ---- distribute, for example, stream test. Select the stream test, ---- distribute, and you get on every single node of that reservation, or even on the system. So you want to do really stress testing. So yeah, that concludes my presentation. So I hope I showed that just a little bit of how powerful ReFrame is, and in doing regression, performance testing, and validation testing. I mean, as soon as you get a bit, if you're not accustomed in Python, I think that as soon as you get a bit, you will very easily write tests in it. And it really hides all the system interaction details. That's good. And it's very, very flexible the way you can compose tests. That's, I think, the big advantage of this DSL that we have written there. And the runtime is also quite efficient. So yeah, you just don't submit tests and forget them. The framework group will ensure that they finish and will take care of comparing the results and so on. So yeah, here are some links, and I think we have one question.
Yeah.
All the ReFrame user guides mention the CSCS use case where Grafana was used to store compare historical performance data. Does this type of user still exist today? Does ReFrame have any special sauce to integrate with tools like Grafana or others? Yeah, so yeah, we do still, we have changed actually the backend. We don't use Grafana, but we use like Logsters internally and Kibana. But ReFrame, yeah, still talks and can send data, and we do that currently. And actually, technically, how this happens is simple. So ReFrame needs to talk to a log server to send logs, and for example, there is the gray log format, which was what was supported even before 3 version, the one you mentioned, like with Grafana. So it was setting gray log records, and then it's a matter of different software on how to visualize those. And then we have added some new handlers when we moved internally to Logsters, that basically the handler is called HTTP JSON, which basically wraps the whole test result and sends it as a JSON over HTTP. And as soon as you have like these Logsters HTTP input, I think, plugin, then you can just visualize them. Okay, and yeah, my colleague here, Victor, says that we're going to talk about this in the user lab day. And by the way, this is what my last thing was, that this Friday, if you be in the CSCS user lab day, yeah, make sure to follow this continuous validation of software performance at CSCS. How can you contribute session, where Victor and my colleague Victor and Irene will talk about more on how we are doing testing at CSCS. So yeah, I don't know. I don't have time to show the demo, but the link is there. So in case anybody wants to.
Okay, I don't see any raised hands, but I'd like to thank you, Vasilis. Thanks also to all the team behind the work here at ReFrame.
Yeah, big thanks to everybody.
And thank you.
It wouldn't have been possible.
Yeah. And thanks also people for joining and watching, and you keep in touch either in the user lab day, or you can join ReFrame Slack for more questions. So thanks everyone from my side. I think we can wrap up here.
Thank you all. Bye-bye.
Thank you. Bye.